for today, we're going to talk about how to classify polygons. We're talking about finding the sums of interior and exterior angles. We use that information also to find the measure of an individual angle. A polygon, definition of polygon, is a closed plane figure. Plane figure means that it has to be two-dimensional, in a plane, with sides made out of segments that meet exactly two other sides at their endpoints.
So should we draw?
Can someone tell me why this one is not, this one here is not a polygon? Bryce?
They're not closed.
It's not closed. At this point right here, there's no intersection there. It's opened up. Okay? Megan, you want to tell me why this one is not a polygon? Yeah, because side BC and side AD intersect two other sides at a point other than the end point. I think I said that wrong. They intersect each other at a point other than the end point, and they, because of that, they intersect more than two other sides. Okay, so those are not polygons because of those reasons.
Why is it?
Why is it what?
The second one, polygons, A, B, C, D.
Because it's not closed right
How
here.
come the other one?
It's opened up. It intersects in the middle.
Thanks, Vicky.
Okay, how do you name a polygon? When you name a polygon by its vertices, I should have put this on here, naming by vertices. You name it by vertices. Two examples of the name of this polygon could be FEDCBA, or CDEFAB, or ABCDEF. The key is no matter where you start, if I choose it starting at F, and I choose to go this direction, I have to go all the way around, in order. If I choose to start at C, and I choose to go this direction, that's okay also. I just have to go all the way around in order. And so to name a polygon, you can start with any point, you can go in any direction, but you must go in order. So there's many different names for this polygon. We name it by vertices. So in the homework, when they say name each polygon by its vertices, this is what they mean.
Do we have to give every single one?
No, just give it a name. Question, if you didn't hear that at home, he asked if you have to name every single possible name. And I said no, just one. Name it, starting wherever you want, going wherever you order you want, and don't skip any letters. The next concept is whether a polygon is convex or concave. To be convex, the red drawing, all diagonals are totally inside the polygon. Well, there aren't any diagonals drawn there. So if I'll use green. If I draw all the diagonals I can inside the inside the polygon, there's all the diagonals I could draw. Remember, diagonals connect vertices that are not adjacent.
It's a star.
It's a star, yeah, just like you. So all of these diagonals are inside. Every bit of them are inside the polygon. If we look at the concave one, and I draw diagonals, I draw all the diagonals we have here. Oops, that one doesn't go there. Oh, this one. There we go. I draw all those in there, at least part of these diagonals, these parts out here, are not inside the polygon. And so that makes it concave. I think of this as a polygon that was in an accident. And part of it has been caved in. Okay? This polygon maybe should have looked like this. It got hit and it's caved in. Okay? And so when it got caved in, it looked like this again. So that's a concave polygon. Okay? At least part of a diagonal is outside the polygon. Any questions on convex and concave? Well, if I draw all these diagonals from the vertices like I had up there, at least part of this diagonal is not inside the polygon. It goes outside the polygon. Okay? So it goes outside the diagonal, or outside the polygon, that makes it not a... Anyway, if part of it's outside the polygon, it's not convex, it's concave. Okay? Now, some textbooks,
It hasn't had paper for a while, so there's like a bajillion things in there. And like, somebody printed off like a couple of bird tests or something like that.
I'm not surprised. Any questions on convex and concave? Oh, other textbooks may not use the term concave. They might call it non-convex. So it's either convex or it's non-convex. In this book, we use the word concave. When I was in school, they used the word concave. Okay? All right. This comes from your textbook. I don't remember what page it is, but this table could be copied down out of your textbook. It's special names for polygons. You for sure know a few of them already. Three-sided is a triangle, four-sided is a quadrilateral. Okay? I think you can probably spell triangle, so we'll move to there.
I didn't see what's at the very top.
Names of polygon.
No, there was another, like, number of sides and then.
Yep, and name.
So look like, are you happy?
11-sided figure is not on there. This book chooses not to name that. There is a name. Actually, there's a couple accepted names. When we're done with notes, if you want to accept the challenge, you can use your phone and try to discover what they are. I think there's also another name for a 7-sided figure other than heptagon. Heptagon is what I always use, but I think there's another name for that. And so after 12, there's probably other names. They aren't as commonly known. And so this book, and for sake of my tests and quizzes, we can just call them whatever many sides there are gone. So if there's 16 sides, it would be a 16 gone. Not a 16 of gone, just 16 gone. If there's 20 sides, it'd be a 20 gone. If there's 120 sides, it'd be a 120 gone. Okay? You would write it like 15 gone. That's how you'd write it. Okay?
Is that
Yep, dodecagon. D-O-D-E-C-A-G-O-N. Okay?
Is that 11 at the end?
What? This is an N and an N-gon. Okay? Get out of your book. I'm not overly creative there.
What page is it, you know?
No?
You all know?
I don't know. Lesson 3-4. So then, that leads us into the polygon angle sum theorem. It says the sum of the interior angles of a polygon can be found by n minus 2 times 180, where S is the sum of all the angles, and n is the number of sides. Okay? So I'll pause this while you copy that down, and then we'll do an example or two. So how many sides does this polygon have? 6. So to find the sum of all the interior angles, all 6 of these, we take the number of sides, which is 6 minus 2 times 180. What's 6 minus 2? Someone told me 12 earlier today. They thought I said 6 times. What's 4 times 180? 720. So the sum of all the angles of this polygon are 720 degrees. Now, let me show you why that comes about. If I draw all the diagonals I could from this one vertex, I end up with how many triangles?
Wait, that's not true.
I've heard 3 and 4, so
5, 6, 7.
Wait,
Tim, are you talking about this or something
What?
else?
No, I was talking about something else. Sorry.
Okay. So how many say there's 3 triangles here? How many say there's 4 triangles here? How many say there's 5 triangles here? So those who have the answer, how many triangles are you seeing? Let's try it again. How many of you see 3 triangles here? Everybody's going to answer this time. How many of you see 4 triangles here? Okay. There are 4. If I highlighted them, this is 1. This is 2. This is 3. And this is 4. What's the measures of the 3 angles of a triangle? What do these 3 angles add up to? 180. What do these 3 angles add up to? 180. What do these 3 angles add up to? Are you lost? Okay. Next time, just let me know and I'll gladly answer that question for everybody, okay? And what do the last 3 angles add up to? 180. How many 180s do I have there? 4 of them. How many sides did it have? 6. So if there's 6 sides, there's going to be only 4 triangles. If there was 100 sides, how many triangles do you think there would be? 98. If there's 1,000 sides, how many triangles do you think we could make? 998. There's always 2 less than the number of sides. That's where this formula comes from. 2 less than the number of sides. N minus 2 times 180 will always give us the sum of the interior angles. Always. Doesn't matter what the shape is. This works for all convex polygons. Okay? All right, we have 3 terms that we need to make sure we understand. The first one is equilateral polygon. Well, we learned what an equilateral triangle was. It meant all 3 sides were the same length, right? equilateral polygon means all sides are the same length. There's not just three of them. Equiangular means all angles are the same. And then regular means that all sides and all angles are the same. The term regular sometimes is taken too lightly. When you're talking about a regular polygon, it means this very specifically, that all the sides have the same length and all the angles have the same measure. Okay? Let you copy that down. Now most of you are wrapping this up. A couple things I want to say. It is possible that a polygon is equilateral but not equiangular. It's possible that it's equiangular, not equilateral. The equiangular is really easy to look at. Let's look at this one. A rectangle, right? All four angles are 90 degrees. Yet not all four sides are the same, are they? Right? So it's possible that it's that way. Equilateral but not equiangular. It's possible, I didn't draw that very well, but this rhombus has all four sides the same length, but the angles are not all the same measure. Okay? So it's not automatically that something has all the same sides but not the same angles. It's not automatic that they have the same angles if they have all the same sides. That's what I meant to say. Okay? So all three of these have different meanings. Any questions on those meanings?
That one's a square then.
What's that?
Regular polygon, that was square.
A regular quadrilateral would be a square. Polygon means more than three sides, so or three or more sides. So it doesn't mean it has to be a square, right? Because you guys have all seen this one. If I could have drawn that well. You've all seen this picture. What is that the shape of? A stop sign. It's an octagon. Okay? That's a regular octagon because all of these angles, I mean, it's not really drawn that way, but that's the intent. All those angles are the same. Okay? And all these sides are the same. That makes it regular. Okay? We have another question back there? Nope. Okay, let's end the conversation, please. All right, now put your pencil down for a second. You don't need to copy this down. I want you to see this. How many exterior angles do we have here? 5. And if I highlight angle 3 is made up of that side and this extended side, right?
Right.
That makes it an exterior angle. Same rule as we had with triangles. They also work with polygons. Okay, so that makes that an exterior angle because it's made up of a side and an extended side. Okay? Now, all 5 of these angles are going to add up to some number. Okay? And if I advance this, and I keep making my polygon smaller, and smaller, and smaller, do you agree that those 5 angles in that picture could still be the same as the 5 angles in the first picture?
Yes.
Okay? What do these 5 angles add up to? 360 degrees. So what do you think these 5 angles add up to? 360 degrees. What if I did the same thing with a hexagon? Or an octagon? Or a hundredgon? Is it going to change what these angles add up to?
No.
No, it's not. That leads us to the next rule, which you want to write down. The polygon exterior angle sum theorem.
Big one.
Polygon exterior angle sum theorem. As you write the title down, I'll raise this up some. Polygon exterior angle sum theorem. And this isn't worded exactly like you'll find it in the book. Like it says, no matter how many sides, the sum of the exterior angles, I should have said of a polygon, is always 360 degrees.
What about a triangle?
Same thing. No matter what the number of sides are, the exterior angles always add up to 360. Okay? Always. No matter how many sides. You name a side, the number of sides, it'll add up to 360, the exterior angles. Okay? So if I look at this picture, what do you think the measure of angle 5 is? If this is a regular pentagon. If it's a regular pentagon, what's that mean if it's regular? All the sides and angles are the same. So that means if this is the same as this, same as this, same as this, same as this, then that means this exterior angle is going to equal this exterior angle, is going to equal this exterior angle, it's going to equal this one, and it's going to equal this one. How'd you get that?
You divided 360 by 5.
Yeah. It's going to equal the sum of all of them divided by how many there are. They always add up to 360, and if there's 5 of them, I divide by 5. I get the measure of angle 5 then is going to equal 72 degrees. Okay? That's the easiest way. Now, if the question was, what's the measure of angle 6? We could find the sum of all the interior angles, remember? 5 minus 2 times 180. But Kayla, what's an easier way?
Oh, I just did 180 minus 70.
Yeah, because these two angles add up to what? 180. If this one is 72, then this one's going to be 180 minus 72, or 108 degrees. Okay? 108 degrees. Any questions on that example? You might need me to pause for a minute. Okay? Practice this. What is the measure of an exterior angle of a regular decagon? Do it on paper. What is the measure of an exterior angle of a regular decagon? Just to make sure Timmy knows what he's doing, how many sides does a decagon have? 10. Is that your question, Tim?
What? No, I right.
Try this. Give everybody a chance to do it.
Yeah.
360 divided by 10.
So
that was
Timothy says that there's 360 degrees altogether, and there's 6 sides, so that means 10 sides, which is 10 exterior angles, so he divided by 10, he gets 36 degrees. I would agree with that. What would the measure of the interior angle be for this one, Alyssa?
I don't know.
I already did that one, but I don't know.
Megan, tell Alyssa how you'd find the measure of the interior angle. Yeah, if you look at just a portion of this decagon, it might look like this, and we just discovered this exterior angle is 36. So how do I find that interior angle? Say it again, Megan.
You subtract 36 and 180.
Yep, so 180 minus 36 is? $144. 144. So the interior angle is 144 degrees. The exterior angle was 36. Okay? Couple key terms here. It said regular endecagon. So that told me all those sides and angles were the same. If it didn't say regular, then I can't just divide by 10. I'd have to know what 9 of them were to find that 10th one, right? But this one says regular decagon, so they're all the same. All right. Our homework today, 3 to 75 by 3s. Skip number 57. Oh my goodness, 3 to 75, how many is that? 25. 25 problems minus 1 is? 24.